Welcome to the podcast of HemaSphere, the official journal of the European Hematology Association. HemaSphere's podcast presents insightful, expert discussions about recent hematology publications. We hope you enjoy.
Welcome everyone to this episode of the HemaSphere podcast. My name is Stephen Hibbs and I'm a hematologist and clinical research fellow based at Queen Mary, University of London. And I'm one of the scientific editors for HemaSphere. So I'm joined today by Professor Robert Hills, who's a professor of medical statistics, has been very involved in leukemia trials over the last 20 years, and who's one of the associate editors for HemaSphere. And we're going to be exploring today a few topics about where statistics, hematology, and trials overlap. But Robert, I wonder if to start with, I could just ask you about your own journey, because I noticed that your doctoral research was initially in a field with applications to superconductors. So I'm interested to know, how did you end up moving into health? And did you notice any difference about how health researchers think about statistics compared to those in physics?
Well, thank you. And it's lovely to be here. Hi, Stephen. So that's a very interesting question. And I'm afraid it gets even worse than that, because I wasn't a physicist and I didn't do any experiments. I was a mathematician. And, mathematics is all about proof and truth, whatever it is. 1 + 1 is always equal to 2. If you start with a set of beliefs, then everything else follows logically. That isn't true in statistics. And the reason really it isn't true is that you're dealing with people. And there is a variability in people. So your experiment, if you like, of giving a drug to a person isn't remotely replicable, because every person is different, every person's leukemia is different, and everybody is going to respond slightly differently, and other things in the world are going to intervene. So you have this idea of uncertainty, which is, anathema to a mathematician who is looking at proof and looking at truth and looking at an equation, and an equation is true or not. And even experimental physicists tend to have very, very tightly controlled experiments. So they take their data and they'll fit their curves to it, but they're not too worried about, the variability in the experiment, because they've got their tightly controlled conditions. It's even more controlled than the best controlled lab experiment in medicine, to be honest with you. So there is a bit of a change, and it's all about sort of embracing uncertainty. But the one thing I think that's important, and it is coming from the mathematical training, is the idea of being a professional skeptic. So you never believe anything that anyone ever tells you. You're asking yourself, where's the evidence? But I got into it purely by accident. And I got into it because I did a lot of programming in my younger days in a language called Fortran, which is, I think, now virtually extinct. But in the days before having databases, a lot of the trials units wrote their own software to do the analyses and to store the data. And the language of choice was Fortran. And so I answered an advert for Fortran programmers and came to work at the then Clinical Trials Service Unit in Oxford and started working on a large trial of bowel cancer called Quasar, which is still producing results even 30 years later. But I started working on that, and I found the idea of trying to sort of, as it were, disprove everything far more interesting than the idea of trying to prove a theorem. So it was a bit of a change in approach. It was great fun, and it still is great fun.
So I'm interested in what it's like coming from that background and then working with a lot of physicians, clinicians of different types, and specifically lots of hematologists. Those of us who don't have the same mathematical underpinnings, foundations, do you find that there's certain concepts around statistics that we find particularly difficult to grasp?
I think the biggest thing to understand is this idea that there is uncertainty in everything that we say and everything that we do. And obviously, this is encapsulated in the p-value a lot of the time. But really, the idea is that we're trying to gather evidence of what happens on average. And a clinician, of course, is dealing with the individual case. And so what we can tell you is what we think the likely benefit of this drug is going to be. But it's all about chances. And, if you say this drug is likely to improve your 5-year chance of surviving from 50% to 60%, well, that's fine. But actually, half of the people would have survived anyway without the drug and don't need it. And the 40% of the people who died with the drug didn't necessarily get any benefit out of it either. So it's that sort of idea of dealing with chances and probabilities is quite difficult, I think. And then to actually understand that statistics can be funny things. There's a great tendency to sort of want to drill down into the detail of the data and look at subgroups of patients and things like that. And of course, the experiments are not designed to be able to do that. They're designed to give an average. So I think the two big concepts are the idea that we're dealing with averages and that we have uncertainty. And, we could go on and we could talk for days about p-values, but one of the things about a p-value is that it's not the strength of the effect of the drug, it's the amount of evidence that you've got. So if you run a small trial and you get, 8 versus 10 deaths in it, well, that's pretty close to 9 versus 9. You know instinctively that is not going to be significant. But if I did the same trial and I made it, 100 times bigger and I got 800 versus 1,000 deaths, then now we're talking same drug, just a different size of trial. One has enough evidence and one doesn't. It doesn't mean that it doesn't work in the 8 versus 10. It just means that we can't actually say that it does work. But 800 versus 1,000 deaths is exactly the data that convinced us that when you have a heart attack, aspirin is good for you. So this is exactly the set of numbers in the ISIS-2 trial that was run in the late 80s. And that's a really good trial to look at from that point of view. It's not hematology, but it's a very large, simple trial in the sense that you have a heart attack, you either take an aspirin or a placebo, and at the end of the day, all that people have done is counted the number of deaths. It's very similar to these very large trials like recovery that have been done during COVID as well. It's simple to do. It can be done in the emergency setting and the like. But one thing that was done when it was written up, and it was actually at the request of the Lancet, subgroup analysis was put in to show the dangers of trying to look into subgroups and say things work in this group and not in that group. The subgroup they chose was star sign. And they found that in 2 star signs, there was no benefit of aspirin, but in the other 10, there was a large benefit of aspirin. So fundamentally, either this is a chance finding or astrology really does work. And, I'll leave everybody to decide what they think is the more likely solution there.
Thanks for it. No, I'm interested actually in similar sort of ways in which we might approach statistics. There's this almost mystical idea about the significance of p is less than 0.05, specifically as this kind of like almost magical threshold. And I remember reading an article in, I think it was Science or Nature, somewhere like that a few years ago, that was actually suggesting that maybe we get rid of p-values altogether because they lead to so much kind of magical thinking about this kind of arbitrary threshold, and saying why don't actually we just go for 95% confidence intervals, which in some ways gets people closer to perhaps what's really going on. I just wonder if you've got any comments on that and on this kind of idea of the kind of p 0.05 threshold as this magical truth-telling device.
So yeah, that's a very good point, and I think that even within statistics and statisticians, there are different philosophies about various things. The first thing I probably ought to say is that for some statistical tests, you are largely stuck with a p-value. And that is the strength of the evidence. But you're absolutely right. I mean, p equals 0.05 was invented by a guy called Ronald Fisher in a book in the 1920s. And I think he gets it a little bit wrong as well, because he says, I've got it here, actually. Personally, the writer prefers to set a low standard of significance at the 5% point and ignore entirely all results which fail to reach this level. So he is saying a low standard of significance actually is quite a large p-value. So he's using p equals 0.05 and not p equals 0.01. But if he's saying then that if p is bigger than 0.05, you should ignore the result. Now, we know that that's not a good idea, because the meta-analysis, for example, of things like gemtuzumab ozogamicin in AML, tamoxifen for breast cancer, takes a whole pile of trials that are not significant in themselves, but together the totality of the evidence is strong. So you shouldn't be completely ignoring these things. But his idea here is that p equals 0.05 is a starting point for negotiations rather than the end result, I think. And that, I think, is important, that, you shouldn't start stretching things. If you like, p equals 0.05 is more likely in a trial of M&Ms for whatever disease you want than it is to take two dice and throw a double six. And that's not that uncommon. But I do think that actually there is an awful lot to be said. And I think certainly as time has gone on and as outcomes have improved, that it's not just whether something works, it's whether it works well enough. I think it's important here that well enough you probably need to think about in a number of different ways. There's obviously the cost and toxicity to the patient, the balance between early toxicity and sometimes even early mortality and late benefit. So, there is a balance of benefits and risks going on, which is sort of masked by a p-value. And there is also, I think, particularly, in places like the UK with a finite health budget, there is an issue of what is actually worth doing in terms of value for money as well as everything else. And I think that's really important, is to understand all of those things. And this is where estimation comes in. So you can say, that something is significant. Well, it could actually have an effect that is too small to worry about. What you want to say is that this effect is going to be big enough, even, you really want as a slam dunk, that the smallest possible estimate of the effect here is big enough to be worth doing. And now you're convincing the payers to actually do it.
Yes.
If it's just significant, then there's a possibility that the payers won't do it, because they will say, well, actually, the cost per life year saved is potentially too high because the effect of the drug is so small. So I like estimation. I think estimation is a very good way of looking at things. It tells you sort of, how many people you need to treat to save a life, to give so many life years. And I also like the idea of sort of breaking down these sort of crude composites like overall survival into understanding what's in hematology likely to be an early disbenefit because of giving a toxic drug versus a later benefit. Other diseases, it's the other way around. So, we give anthracyclines in AML, and the risk of the anthracycline is induction death. You give anthracyclines in breast cancer, and the way it's given, there's not a huge rate of induction death, but there is actually a late risk of developing AML and heart disease with it. So the different time windows, the horizons differ according to your setting. And that's important to understand. I think as we get better and better and better, and the drugs get more and more expensive for more and more marginal benefits, understanding what you can do with a basic drug and what you can do with an expensive drug is very important. Not least because you'd like to deploy the expensive drug, and the toxic drug in particular as infrequently as you have to. And this is why, there are still debates over the value of transplant in certain areas of hematology. It's because obviously the benefits are not gigantic. They're moderate. There are disbenefits, quality of life, transplant-related mortality and morbidity. And you have to say to yourself, well, where's the balance point in order to give somebody a transplant and not do more harm than good? So that's where estimation comes in. And estimation is much easier to tell people what we think the balance of benefits and risks are. That being said, of course, when we design our clinical trials, our definition of sample size calculations is working entirely on P is 0.05. And that is, that's maybe something that can be changed over time and actually look at it from the point of view of being able to estimate a treatment effect with a certain degree of accuracy.
Yeah. So I'm interested that you've done work in clinical trials for 3 decades now. Have you noticed any trends in how clinical trials how specifically statistics in clinical trials have been used or presented over that time?
So, yeah, there have been some trends sort of, as it were, good and bad. And the good trend is, in a sense, trials are much more likely to have a proper sample size calculation, and we are much more likely to see hazard ratios and confidence intervals so that you can actually see the effect size that's going on. There are some trends that are much more difficult. One of them is, as it were, not the fault of the trialists at all, but the fault of the funders, and that's the ability to get long-term follow-up. And long-term follow-up is absolutely crucial, I think, because we want to know that there are no late effects or how long these effects last for. If you're merely delaying a recurrence by 6 months, but the outcome after the recurrence is the same, that's very different from preventing a recurrence or turning an early recurrence, which is bad risk, into a late recurrence, which is good risk. So there are all sorts of things there that long-term follow-up helps. I think we're much better in hematology, and I think hematology has probably led the way in terms of getting samples associated with clinical trials. I think they're very good. And of course, outcomes have improved an awful lot. So that changes the question, again, from one of purely survival into survivorship. At what cost are you actually living that little bit longer? So that means that issues like quality of life become ever more important. Quality of life, you could argue, is much less important if nobody is surviving. That being alive, even in a less health state, is better than being dead. But when you're actually looking at marginal improvements, quality of life becomes very important, I think, there. The other thing, of course, is with all these samples, we're discovering that the conditions that we sort of lump together under the heading of AML, ALL, etc., are not just one thing. They are a variety of things. So we now think of APL, acute promyelocytic leukemia, as different from AML, and it is. And from a statistician's point of view, it's different because you treat it differently. It's a different condition because actually the approach you go in with is different. So it needs a different look. And, the introduction of ATRA and arsenic has transformed it from a very bad risk subtype into a very, very good risk group. And I think that there is an understandable desire to try and look at these sort of targeted therapies and to try and look at what mutations are actually driving the leukemia and what mutations drive the response to therapy. And that becomes very difficult because when not looking at breast cancer or lung cancer or bowel cancer or heart attacks or childbirth, where you've got tens or even hundreds of thousands of cases you can get hold of every year. We're looking at generally, AML 3,000 cases a year. A lot of those are quite old, and so the treatment options are limited. So you end up with dividing what's already quite a small cake into even smaller and smaller pieces. And it becomes very difficult then to run randomized trials. And so you're really relying on a single-arm study, which is in a sense a case series. And the decision to enter the trial is now something that is important. A 40% response rate in good risk patients is going to be interpreted very differently from 40% in bad risk patients. So until you know what risk these patients are, you can't interpret it. And that, of course, was the benefit of randomization. It doesn't matter about the selection going in. What you're actually looking at is the difference between them. And generally speaking, it's quite rare that you find that the decision to enter a trial actually affects the effectiveness of any treatment, that they are generally affected in a much wider population than may necessarily have been in the first trial. In these small case series of patients treated with, a targeted agent, it becomes much harder to understand what's going on. And I think it's then very easy to either find a comparator group that does very badly or a comparator group that does quite well. So which one do you believe? It becomes very hard. And I think that's a real challenge going forward, is that if we don't all band together, then we're not going to be able to get reliable evidence that we can understand going in.
I want to spend the last part of the podcast thinking a bit about learning statistics, because it's something that often, I know, speaking certainly for myself and for lots of my colleagues, we feel quite nervous about and can feel, difficult to know where to get started. And perhaps just to kind of set the scene on that, I'd be interested to know if you look back on a kind of early career version of yourself, so when you were first new to trials and healthcare and your own understanding of statistics then, is there anything that you can see you've learned that's changed in your approach to understanding how statistics works over that time?
Yeah, I think there's a big difference, and actually, it's not necessarily to do with statistics for me, and I think it's the interaction between the clinician and the statistician. The equations in statistics are, generally speaking, quite straightforward and simple. Again, there's a lovely quote by Geo Ashley. Like other occult techniques of divination, the statistical method has a private jargon deliberately contrived to obscure its methods from non-practitioners. I think this is probably the inbuilt skeptic in me. The more jargon there is, the less intellectual content there is behind it necessarily. Therefore, it's all about being able to have a conversation, and have a conversation in, real words with people. And, if I were to say, the thing that I've learned is that as a statistician, you've got to talk to the clinician and understand as much as possible of what they're doing. It is teamwork that, again, it's important to get the statistician involved early on in the idea, because, if the experiment has gone wrong, you're just doing a post-mortem. But the statistician doesn't necessarily understand the clinical relevance of what's going on. So being able to understand that enables the right question to be asked. And the important thing is ask the right important question and answer it reliably and in a way that people are going to be convinced. So yes, you're absolutely right. The jargon of statistics puts a lot of people off. And I think this is one of the reasons where the idea of significant and not significant is, very, very attractive to people, because it's a straightforward yes, no. I think we've all seen examples where things have been written up in such an obscure and complicated way. The ultimate aim here is not to get a number at the end of it. It's to actually save lives, improve people's outcomes. So if you do something that nobody believes, what's the point of doing it? You've really, you've taken the goodwill of the participants in your study and said, well, I don't care, I'm just going to do what I want to do with this, and I'll come up with some numbers. It doesn't matter if it changes practice. So the simple methods are always the best from that point of view because they can be explained. But I do think it's important that, every clinician really should have a statistician that they can go to and talk to. Alan Burnett always talked of it as a walk on the beach. And it's absolutely right that rather than, doing this by email or doing anything like that, the more informal way of looking at it, the better. And I've learned an awful lot about, hematology and the like from some very, very, important hematologists over the years. And I think that what's also important here is that, that the statistician justifies their existence to the clinician or the lab scientist as to what's going on. It's a specialist occupation being a statistician. So, you don't expect me to see a patient. So I shouldn't expect you to have to analyze data. And to be honest with you, you probably shouldn't analyze data because, it's a question of experience. And that's the whole thing for me is that, it's a partnership and it's going forward. So, the thing that I learned and I was very, very fortunate to be exposed to is people who will talk about their subject.
Yeah.
And so a statistician should listen to clinicians and clinicians should cross-question statisticians, because if we can't explain it, then maybe we don't understand it.
Thinking kind of along that note of, I guess, being aware sometimes of our own level of expertise or non-expertise in reading statistics. One thing I'm aware of is when I'm reading a clinical trial report, I've often got this fear that there's some sort of trickery going on. There's something that's kind of happening, but it's a skepticism in a clever way where you can kind of really unearth it. It's more of this cynicism that's like, can I trust this? Can't I trust this? And obviously there's lots of different parts to reading clinical trials and it's not all about the statistics, but I guess I'm just kind of wondering what your advice would be to the clinician who fears that the wool's being pulled over their eyes with stats in some way or another, doesn't feel like they really know exactly what they should and shouldn't be looking for, doesn't know how much they can trust the kind of due diligence has been done with the statistics before they're reading it, kind of wants to get beyond just that general sense of doubt to something a bit more solid.
Generally, if you feel the wool is being pulled over your eyes, it's probably true, because if there is no need to pull the wool over one's eyes, then fundamentally you don't do it. But the biggest thing in reading a paper is trying to think, well, how can somebody cheat? I would go back to sort of various series on, there are some in the old BMJ, there are some in various places, and ask, how would I cheat if I was doing this thing? And if it's not explained that you can't cheat, then start to distrust it. It's okay to be skeptical. I mean, that's what a statistician does. You're the optimists and we're the pessimists.
Thank you. So just finally then, I guess now thinking about those who are involved in clinical research and perhaps trying to perhaps have got a statistician they're talking with, perhaps haven't managed to find someone yet, but just feel like they need to upskill a bit on their understanding of medical statistics to just be able to, even if it's just having better conversations with the statistician they're working with. Where's a good place to start? Where's a good place to go first with wanting to take their learning forward?
It's very, very good, and I think quite a complicated question as well. I say there are some very good articles that were done by Doug Altman and Martin Bland over the course of about the last 30 years again, which are called the Statistics Notes in the British Medical Journal. There are other ones available in other journals as well. There are some quite nice little books like Statistics at Square One, Statistics with Confidence. I genuinely think that the best way is to actually question somebody over and over again. If you don't get it, if you've got somebody, just find somebody, latch onto them, Statisticians are great. We'll always work for alcohol. So you buy us a beer and we'll do anything basically. I mean, food, beer, coffee. We're very good. If you give us something like that, then we'll talk for hours and hours and hours.
Thanks so much. So, Robert, I want to thank you for your time this morning. It's been a really useful discussion.
Thank you.
And I want to thank all of our listeners for listening to the HemaSphere podcast today. And we'll be back with you with another episode soon.
Thank you for listening to this episode of the HemaSphere podcast. All of HemaSphere's content is open access and can be found at www.hemaspherejournal.com. We hope you will join us for future podcast episodes.